lecturer at the Faculty of Technion since 2022, and until 2022, he was a postdoc researcher in Ludwig Maximilian University of Munich, and before that, he was a postdoc at TU Berlin, and he did his PhD in Tel Aviv University under the supervision of Professor Nir Shochan. And his research interests are in the area of basically mathematics of deep learning, graph deep learning, and explainabilities in deep learnings. So today he will share with us his recent works on regularities of graph neural networks, which I believe is of interest to a lot of us here. So please join me in welcoming Ron.
Okay, thank you for the introduction and thank you for the invitation. So what I'm going to do, I'm going to build a structure on the input space of graph neural networks. Namely, I'm going to build a metric. And this metric reveals that graph neural networks behaves regularly. And from this, we can prove various results like universal approximation and generalization theorems and more. And also derive some applications. So, okay, so the different parts of this talk are from works with my different collaborators. So I suppose in this seminar, I don't need to convince you that graph neural networks are important, both in the academy and the industry, right? Because often the data is not given to us as a point in a Euclidean space, but it's given as a graph. Okay? And in my research, I developed mathematical foundations for graph machine learning and also try to derive applications of the theoretical insights. So let's compare the analysis of graph neural networks to analyzing standard neural networks like multi-layer perceptrons or convolution networks. So a standard neural network is a function that takes a vector in some vector space, right, which is predefined, and returns a vector in another vector space. And the fact that we have the domain is regular, right? We have the Euclidean metric, allows us to derive various theoretical results like universal approximation theorems that tell us that any continuous function can be approximated by a neural network, and generalization theorems that tell us that if we have a training set and we train the network, we are guaranteed that the statistical risk is close to the empirical risk. And in all of these results, you need to use the structure of the input space of the neural network. So you use stuff like compactness, covering number, how many balls of a certain radius you need to use to cover the whole space. You use continuity of functions over the domain, and so on. Now, if you compare it to the graph neural network situation, here a graph neural network is a function that maps a graph with node features. This is the input space. Right? So we call it a graph signal. The signal is a mapping from the nodes to features in some Euclidean space, and returns either another signal on the same graph or just a feature for the whole graph in some feature space, in some Euclidean space. Now, the challenge here in developing theory is that it's not clear how to define a metric on the input space, right? Because graphs can be of any size and any topology. So how do you compare a general set of pair of graphs? Now you can, in many past works, there were different approaches. For example, you can look at the adjacency matrix of the graph and fix the size and just think about it as a point in the Euclidean space. This is related to equidistance. And in many of these approaches, the problem is that you get a metric which is too fine. Too many graphs are far apart in this metric. So graphs that for us look like they describe the same phenomenon can be far apart in these metrics, and also they are not compact, and it's difficult to develop theory. In some sense, they are not very natural. So the goal in this talk is to construct a metric on the space of all graph signals that has the following properties. First of all, the metric should give a meaningful notion of graph signal similarity, that in some sense describes our intuition. So graphs that we expect to be close because they somehow describe the same thing are going to be close to each other in this metric. And the metric should have good properties. We are going to prove that it is the space of graphs under this metric is compact, or more accurately, it is dense in a compact space on the one hand, and on the other hand, message passing networks are Lipschitz continuous with respect to this metric. Okay, so in some sense, these are two competing requirements, because to be compact, everything has to be close to each other, in a sense. But then, if things are close to each other, it's more difficult to be continuous. It could be that the space of message passing network is given to me. I'm not defining it with respect to the metric. So it could be that things are too close in the space that message passing networks, quote unquote, have jumps. Right? So the more compact the space, the more difficult it is to be Lipschitz continuous, but still we are able to prove both properties. And these two properties together allow us to prove various results like generalization theorems, universal approximation, expressivity, sampling, and more. Okay, so just to make sure that we all understand what we're talking about, so just to level the playing field, let me give you a short description of what message passing networks are. This is the type of neural network that I focus on. Right, so message passing networks are most practical examples of graph neural networks are either special cases. Most of them are special cases of message passing networks, and some of them are slight extensions. So in a message passing network, we have a graph with a signal. So let's plot the values. Let's represent the different values of the features by different colors. And in each layer of the network, we update the feature value of each node according to the feature values of its neighbors. And we do it by defining a trainable function called the message function. So let's say I want to update the value of this node. I take the message function, I plug in this central node, and the feature at the central node and a feature at the neighbor, right? And I take the same message function and I apply it on all of the neighbors. And we interpret this as messages sent from the neighbors to the central node. So the central node looks at all of the messages and then needs to combine them or aggregate them. So typical choices of aggregation is to do average aggregation or sum aggregation or max aggregation, as long as it is an operator that is invariant to permutations, because the edges don't have a natural ordering. Okay, and then we apply the same message function to all of the nodes, to all of the neighborhoods. And this is why we can think about it as a sort of nonlinear convolution, because we use the same template everywhere. And then the aggregated message is plugged in another trainable function, which is called the update function, that takes the previous value of the node and the aggregated message. Okay, and then we have many layers of this, and each layer is based on a different trainable message and update function. So I'm going to focus in this talk on normalized sum aggregation. So what we do is we sum the messages and divide by the degree of the graph, the total number of nodes in the graph. So usually the popular types of aggregation are sum aggregation and max aggregation. And normalized sum aggregation is related to sum aggregation, but it's not sensitive to the size of the graph. So in data set, so usually the performance of normalized sum aggregation is comparable to sum aggregation. So this is the type of aggregation I'm going to focus on in the construction. Okay, so we are going to build a metric between graph signals that has the following interpretation. Two graph signals that look like they were sampled from the same stochastic block model are going to be close to each other. So what is a stochastic block model? This is a generative model of graphs where we consider a set of classes, and between each pair of classes, we consider a probability of having an edge between the classes. And we generate a random graph by sampling nodes randomly from the different communities and connecting each pair of nodes with probability given by the stochastic block model. Okay, so we can randomly sample graphs of different sizes from the same stochastic block model. So these are two examples. Okay, so in this picture, I can tell you that this is the generated graph is a random variable. But I can also tell you that this picture is actually of a deterministic graph. And visually, it looks like this deterministic graph, right? It behaves like it was randomly sampled from the stochastic block model, even though it is deterministic. Because in some sense, the densities, the edge densities between the blocks somehow behave like the expected edge density from the stochastic block model. Okay, so then you can ask yourself the following question. Given a deterministic graph, is it always possible to find the stochastic block model such that the graph looks like it was randomly sampled from the stochastic block model? And the answer is yes. This is called Zemeredi's regularity lemma. And it says exactly that. The lemma says that any graph, for any graph, you can find the partitioning of the nodes to classes such that the graph looks like it was sampled from the stochastic block model based on these classes. And the nice thing about the lemma is that you don't need to know anything about the graph in order to know how many classes to use. The number of classes only depends on how much you want the graph to look random and not on the size of the graph and not on anything else. So I'm going to give you a variant of this lemma in the next slide. And I'm going to define what it means for a deterministic graph to look random-like. Right? And this lemma was proven by Zemeredi in 75 for bipartite graphs, and then he extended the proof for general graphs in 78. And the lemma has many extensions and many types of proofs. For example, Noga alone gave the first constructive proof, so some polynomial time algorithm that computes this partition. And the lemma also has many applications in pure mathematics. You can prove many theorems in graph theory and number theory using the regularity lemma. Okay, so let me describe one variant of the lemma, which is called the weak regularity lemma. It was proven in 1999 by Fritz and Kanan. I think it's a very nice lemma, so I think it's worth going through all of the definitions and construction, and it's also relevant for this talk. Okay, so what we want to do, we have some graph, it is deterministic, and we want to partition the nodes to non-intersecting classes in such a way that the densities of edges between each pair of classes or each pair of sets of nodes behaves in some sense like the expected number of edges if the graph was random. So we need to give some definitions about densities of edges between sets of nodes. So let's denote the set of nodes, the node set by V. And for each pair of node sets U and S, let's denote by EGUS the total number of edges between nodes in U and nodes in S in the graph G. Okay, so now given some partition of the set of nodes to classes, V1 until Vk, which are non-intersecting, if the graph, we can define the stochastic block model that in some sense best approximates the graph using these predefined classes. Okay, the probability of having, you define the probability of having an edge between Vi and Vj as the number of edges in the graph between Vi and Vj divided by the maximal possible number of edges. Right, so in a sense, this is the best stochastic block model to approximate the graph if you consider the partition V1 until Vk. Now the graph is deterministic, right? It wasn't sampled from anything, but if the graph had been randomly sampled from this stochastic block model, we could have computed the expected number of edges between each pair of node sets. Okay, so for each pair of node sets U and S, if the graph was randomly sampled, the expected number of edges between U and S would have been the following formula. So you need to sum over all of the blocks, namely all of the pairs of classes. You see how many nodes in U there are in the first class, times how many nodes in S there are in the second class, and you multiply by the probability of having an edge between the different classes. And this would have been the expected number of edges. Okay, so this gives us a way to define how much the graph looks random, because the graph has an actual number of edges between U and S, and you can compare it to the expected number of edges if the graph was random. Right? The difference between these two is how much the graph looks random. So this is called irregularity. Irregularity measures how much the graph doesn't look random, given a partition of the nodes to classes Vj. Right? So what you do is you take the pair of node sets that maximize the difference between the actual number of edges between the two sets and the expected number of edges. Okay, so the smaller irregularity is, the more random the graph look, the more random like the graph is. And now the weak regularity lemma says that we can always find a partition in Vj such that the irregularity is small. Okay, so for every epsilon, where epsilon is going to be a bound on the irregularity, and every graph, there is a partition of the nodes to classes. And then the important thing is that the number of classes only depends on epsilon. It only depends on how much I want the irregularity to be small and not on the graph itself, such that the irregularity with respect to this partition is less than epsilon. Okay, so this is the weak regularity lemma. In summary, it says that even though deterministic large graphs may look complicated, they're actually regular and behave like random graphs that were sampled from stochastic block models. Right, so there is no way I can give you pen and paper and you can try to plot a graph that looks as deterministic as possible. It's impossible to do it. I can always find a stochastic block model that looks like the graph was sampled from this stochastic block model, and the number of blocks just depends on how much I want the graph to look random. So we are going to derive a metric based on irregularity, right? Two graph signals are going to be close in this metric if they look like they were sampled from the same stochastic block model. But for that, we need an extension of the regularity lemma. We need two extensions. So first of all, because we are interested in graphs with node features, we want to extend the regularity lemma to graph signals instead of just graphs. And the metric that we are going to develop, the space is not going to be complete. You're going to have some Cauchy sequences that don't converge. So we want to take the completion of this space, and in some sense, the limit objects are going to be graphs with continuous node sets, not discrete node sets. So we also want to extend to graphs with continuous node sets, and these are called graphons. And by the way, for us, a stochastic block model is a set of classes, and also for each class, there is a feature that you sample when you sample, because you want to sample a graph signal, not just a graph. Okay, so what is a graphon? As we said, this is a graph with a continuous node set. The node set is the interval 0 to 1. And a graphon is a measurable function from pairs of nodes to weights. Right? So the interpretation of Wxy is the edge weight between node X and node Y. Okay, and we use the node set 0, 1, the interval. And this is very general because graphon theory is a theory of measurable functions, not continuous functions. So we don't use any metric or any topological property of 0, 1. 0, 1 is not the one-dimensional line. 0, 1 is the measure space 0, 1. So it's the standard probability space. And as a measure space, it is equivalent to many other spaces, to 0, 1 to any power, in any dimension. It's equivalent to any compact manifold and any Polish space and so on. So limiting the space of nodes to be 0 to 1 is not a limitation. This is the generic case in a sense. Okay, so graphons can also be seen as generative models of graphs. a random graph is randomly generated from a graphon by sampling independently and uniformly the nodes from the interval 0, 1, and connecting each pair of nodes according to the probability given by the weight of the graphon, Wx and Xn. And also, graphs can be seen as special cases of graphons. So you can embed the space of graphs in the space of graphons. What you do is you take the adjacency matrix of the graph and extend it as a piecewise constant function over 0, 1 squared. So you get a piecewise constant graphon. And we think about piecewise constant graphons as graphs. So anything we prove for graphons is going to be also true for graphs as a special case. Okay, so Lovas and Zagedi proved in 2007 an extension of the weak regularity lemma for graphons. And in this situation, it turns out that irregularity is a norm. So you remember irregularity is something that tells you how much a graph looks random. And for graphons, you actually get a norm, which is called the cut norm. So given two graphons, the cut norm of the difference between the two graphons is defined to be as follows. You take pairs of node sets in the node set 0, 1, and you compute the average edge weight in the first graphon, the average edge weight in the second graphon between these two sets of nodes, and you subtract, take absolute value, and this is called the cut norm. Okay, so it turns out that irregularity is a special case. If you take W1 as a graphon induced from a graph, as a piecewise constant graphon from a graph, and W2 as a stochastic block model, namely a piecewise constant graphon that comes from a stochastic block model, then this is the difference between W1, W2 in cut norm is exactly irregularity. Okay, so the cut norm describes how much the two graphons look like they came from the same stochastic block model. Now, for us, we want to work with graphons with signals, because this is the input space of message passing networks. So we extend the definition to graphon signal cut norm. So given two graphons, and now the signal is a function from the node set 0, 1 to some feature space. And just for simplicity, let's take R as the feature space. So the cut norm of the difference between the two graphon signals is the sum of the cut norm of the two graphons plus a definition of cut norm for the difference of the signals. So here we define it as follows. We take the supermove over the node sets. We take the average of the first signal in the set minus the average of the second signal on the set with absolute value. So cut norm of graphons is not equivalent to any LP norm, but you can show that this definition of cut norm of signals is actually equivalent to the L1 norm. You can bound this from above by the L1 norm of the signal and from below by 0.5, the L1 norm. So you could replace in the whole theory the signal norm by L1, but you get nicer bounds and the proofs are nicer if you use this definition that we proposed. Okay, so the last thing we need to do is, because we are interested in graphs, and graphs don't have a natural ordering of the nodes, we want to define a metric or a distance which is permutation invariant. It doesn't depend on the ordering of the nodes. So we define the graphon signal cut distance, which is the cut norm up to the best permutation that aligns the two graphon signals, right? So you take one of the graphon signals, you permute the nodes in such a way that the distance is minimized, and you take the norm. And this is how we define cut norm. And the only thing is that because the node set is not discrete, you don't call it permutation, you call it a measure preserving bijection. So it's a one-to-one function that preserves all of the measures. And this is how you model permutations in measure spaces. Okay, and because this, we extended this definition from irregularity, it has the same interpretation. the interpretation of the cut distance between two graphon signals is how much the two graphon signals look like they were sampled from the same stochastic block model. Okay, so this is the metric we're interested in. And now I was able to extend the regularity lemma to graphon signals. Okay, so now the lemma says the following thing. For every graphon signal and every error tolerance, there exists a piecewise constant graphon signal, namely a stochastic block model. On the equipartition to intervals, and the number of intervals only depend on the error tolerance and not on any property of the graphon signals, such that the cut distance between the graphon signal and the stochastic block model is bounded by epsilon. Okay, so let me give you an illustration. So this is an example of a graphon signal. I plot the graphon in grayscale. This is 0, 1 times 0, 1. And the signal is plotted on the diagonal in color. And the theorem says that there is always a permutation of the node set such that the graphon signal looks like a stochastic block model. Okay, obviously, I exaggerated the situation here in this picture, but that's the theorem. And now, if you think about it, what is nice about this version of the theorem is that it's not only that the number of classes don't depend on the graphon signal, but the classes themselves don't depend, because the whole analysis is up to permutations. We can always take the partition to be the intervals. Okay, so the partition is predefined. Given epsilon, the block structure is predefined. And in some sense, this means that I took the space of all graphon signals, which looks huge and infinite dimensional, and I approximated it by a finite dimensional space, because the space of all stochastic block models with a fixed block structure is finite dimensional. Just need to define all of the weights here, and you have a finitely many. And from this, you can prove that the space of graphon signals under cut metric is compact. It's compact, and we can bound the covering number. So for each epsilon, we know that we need to use this amount of balls of radius epsilon to cover the whole space. Okay, this is very large, but still the space is in a sense small. So think about it like this. We started with a space that looks really large, the space of all graph signals. It's definitely infinite dimensional, and it's because the size of the graphs is unbounded. But still, now we see that this space is dense in a compact space. By the way, in the regularity lemma, this bound is essentially tight, in the sense that if you decrease this constant 2 to something smaller, for every epsilon, there exists a graphon signal such that there is no stochastic block model with less than this number of blocks that approximates it. So this is essentially tight. This bound, I don't know if it's essentially tight or not. This is an open question. I initially thought it was tight because of the tightness from the regularity lemma, but I'm not sure anymore, because this bound comes from quantizing the weights of the stochastic block model. Yeah, but the situation is more complicated, so I don't know if this is tight or not. Okay, so we now know that there is some interesting metric such that the space of graphon signals is compact. But this is not useful it's not useful still unless we know that message passing networks behave nicely with respect to this metric. Okay, because it could be that I took a metric which is too compact, and then message passing networks are not continuous even. So it's not going to be helpful. So the next thing that we want to prove is that message passing networks are Lipschitz continuous. So again, these are two competing requirements, right? Because the smaller the space, the more close by all of the points, and then it's more difficult to be Lipschitz continuous because you have more jumps. Okay, sorry. Okay, but before we do that, we first of all need to extend the notion of message passing from graphs to graphons, right? And there is a canonical definition that there is a natural way to extend message passing from graphs to graphones. So first of all, the message function, there's nothing to extend because this is a function that takes two node features. And the node features don't care if they come from nodes that live in a discrete space or a continuous space, right? So message function is defined as is. The only thing you need to extend is the aggregation, and you extend normalized sum aggregation to integral aggregation. What you do is you take all of the messages sent to some node, and you integrate them against the edge weights that come from the graphon. And then you can show that this is in some sense the canonical definition, because in case that we start with a graph and we induce a graphon from this graph, a piecewise constant graphon, and then we apply integral aggregation, we get exactly the same thing as doing normalized sum aggregation on the graph and then inducing a graphon. Okay, so this is the natural extension. Okay, so standard message passing is a special case of message passing on graphons. So anything we prove for message passing on graphons is going to be immediately true also for graphs. Okay, so then I was able to prove that message passing networks are Lipschitz continuous in cut distance. So if you have two graphon signals and you take a message passing network and you apply it on the two graphon signals, and then you compute the cut distance of the output, this is bounded by the cut distance between the two graphon signals up to a constant which is guaranteed to exist. And this is called this is the Lipschitz constant of the message passing network. Now, the only assumption that we need to take here is that the message functions are Lipschitz continuous. And this is a very, very reasonable assumption, because otherwise, right, if you want to be able to train the network, it has to be differentiable. So you need to assume something like Lipschitz continuity. So this is a very mild assumption. And that's the only assumption you need to take. Okay, and this Lipschitz constant depends on the constants of the message functions. Okay, the way to prove it is somehow you look at the types of operations that you do when you pass messages, and somehow they look similar to the types of operations that you do when you compute cut distance. Yeah, and from this you can prove Lipschitz continuity. Okay, so now we have two good properties. First of all, the input space of message passing networks is compact, and on the other hand, message passing networks are Lipschitz continuous. So these two things together allow us to prove many corollaries. So first of all, we can prove a generalization theorem that says that if you have a training set and you train a network, then the statistical risk is guaranteed to be close to the empirical risk. So let me give you a very short reminder from statistical learning, just to make sure that we remember the concepts. So usually in statistical learning, we think about the data as living in some probability space, right? So we have the probability distribution of the inputs. And let's suppose that for each input, namely for each graph signal, there is a ground truth output. For example, if I do classification. So we define a loss that takes 2 points in the output space and tell me how similar they are. And the risk is defined to be the expected loss. Right? So you take the neural network, you apply it on your input, it gives you something. It should have given you yx, the ground truth, but it doesn't give you exactly yx. And the loss is how much the neural network is accurate specifically for this input, and then you average it over all potential inputs to the network. This is the risk. Now we cannot minimize the risk because we don't have access to yx, to the ground truth. And also we don't have a good model for the probability distribution. So what we do in practice, we assume that there is a training set that was randomly and independently sampled from the probability space G, and then we minimize the empirical risk, the sum over the losses for the training data. Okay, so in some sense, it seems like the empirical risk is a sort of Monte Carlo approximation of the statistical risk, But this is not, it's a little bit more complicated than that, because the neural network is also a function of the samples, of the training set. The training set is randomly generated, and the neural network is fitted to the training set. So I cannot treat it as a fixed function. So in uniform generalization bounds, what we do is we try to minimize, to bound the difference between the statistical and the empirical risk over the neural network that maximizes this difference. Okay, and now the difference from standard Monte Carlo theory is that because the network is not fixed, there is no, we don't have one event in which the sample set is good, right? For each network, there could be a different sample, a different event in which the approximation is good. And then you need to intersect all of these events, and this complicates the situation. Okay, so I was able to prove that for message passing networks, the difference between the empirical and statistical risk decays as the number of graph signals increase in the training set. The nice thing here is that you don't need any assumption on the data distribution, right? The data can be distributed as any way you like. You don't need any assumption, and also you don't need any assumption on the architecture of the message passing networks. You don't have any restriction on the type of functions and the number of parameters. The only restriction is that your Lipschitz continuous. And also you need to fix the number of layers. Okay, so this function, psi inverse of n, is decaying where the number of training examples n go to infinity. Right? So this shows that the statistical risk converges to the empirical risk. So if you compare it to past works that analyzed or bound the generalization gap, in all of the past works, you need to have many assumptions. So you have assumptions on the data distribution. For example, you assume that the degree of the graph is bounded. And you typically also have assumptions on the architecture. For example, you assume that all of the message functions are shared in all of, so you have only one message function applied on itself many times, or that the message functions are linear, and you assume that the number of parameters is bounded, and so on. And for us, we don't have any assumption, but the decay is much, much slower. It's something like log n, instead n to the negative half. So one way to interpret our result is it shows us what happens if all of the assumptions from other works are not met in practice. And these assumptions are often simplistic and they are not met in practice. So we are guaranteed some sort of convergence, even if none of the assumptions are satisfied from other papers. Okay, another application of the compactness of the graph on signal space and the Lipschitz continuity of message passing networks is a sampling theorem that says that if we have a graph, let's say it's a large graph, and we randomly subsample it by subsampling the nodes and considering the subgraph, then applying a message passing network on the small graph approximates the message passing network on the large graph. And again, we don't need any assumption whatsoever on the graph and the signal. It applies for any graph and any signal. Right? So this is something people do, because in many applications, the graph is so big, there is no way to fit it in memory. Right? Like companies like Google, Facebook, they have graphs of hundreds of millions of nodes, and they need to subsample them. And there are different ways to do it. And this is one justification of subsampling a graph under no assumption on the data. Okay, so now let's talk about expressivity and universal approximation. So what we did until now, we showed that if two graph signals are close to each other, then the outcome of any message passing network is also going to be close. So now we want to prove something. We want to prove an if and only if version of this. We want to prove that two graphs are close to each other if and only if any message passing network applied on the two graphs gives a close result. And this we were able to prove only in the special case where the data is only a graph without a signal. And for that, we need to relax the notion of cut distance. So you remember that cut distance was defined as follows. You took the two graphons, W1, W2, and on one of them, you applied a permutation that minimized the cut norm. And this was the definition of cut distance. And now we relax, and this permutation is a sort of alignment. You try to align the two graphons as much as possible to somehow minimize the distance. So now we relax the notion of alignment from a hard alignment to a soft alignment. We replace the permutation with a Markov operator. You can think about it as taking the nodes and splitting them to different small parts and then mixing everything together and then doing the alignment like that. Okay, so if you define a distance using Markov operators, this is called tree distance. And now tree distance has the if and only if result. So two graphs, the application of any message passing network on two graphs is going to give me something close, if and only if the two graphs are close. So this is already an expressivity result, right? It tells me what is the separation power of message passing network. And we can also prove a universal approximation theorem. So now we can prove that for every continuous function that takes graphs and return features like numbers over tree distance, there is a message passing network that approximates it. And in some sense, the tree distance, the topology that comes from tree distance is the finest topology that allows universal approximation. If you take a finer topology, right, a topology in which things are more far apart, then it is easier to be continuous, right? Because the more far apart the points in the space are, the easier it is to be continuous. You have less jumps, so quote unquote, for functions. And then you have too many continuous functions and you cannot approximate them with the message passing network. So the tree distance topology is the finest topology in which you have universal approximation. Okay, so what we discussed until now are theoretical applications of the regularity lemma and the Lipschitz continuity of message passing networks. But we also developed practical applications, so designs of new neural networks. So let me discuss very shortly a paper called Approximately Equivariant Graph Networks. So here we have the following situation. We have a fixed graph, and the data set consists of many different signals on this fixed graph. Okay, so for example, think about a traffic network. So the graph is fixed because it represents the map of the roads. But you have, and the signal is how many cars there are in each location along the road. So the signal changes over time. So you have many signals, but only one graph. Now in such a situation, because the number of nodes is fixed, what you can learn, you can use a multi-layer perceptron, right? Because the dimension is fixed. In principle, if you want to do traffic prediction and the graph is fixed, you can just take the signal, plug it in a multi-layer perceptron and see what comes up. Now this is going to overfit because you have too many trainable parameters. And the typical approach in geometric deep learning to reduce the number of trainable parameters is to look at the symmetries of the problem and define a neural network that respect the symmetries, that commute with the symmetries, and then the neural network depends on less trainable parameters. So the natural symmetries for graphs are automorphisms, self-similarities of the graph. The problem is that automorphisms are very sensitive to graph permutations. You can have a graph with a very rich symmetry group with many automorphisms, and then you delete only one edge and you completely ruin the whole symmetries group. it becomes very small and trivial. And because graphs in application are natural phenomena, right? They're noisy and they come from some stochastic process. Typically, natural graphs don't have interesting symmetries. They have very trivial symmetries, very small symmetries, like small reflections. And considering the symmetries, the automorphism of graphs is not going to help me reduce the number of trainable parameters. But what we can do is we know that any graph can be approximated by a stochastic block model using the regularity lemma. So given our graph, we can approximate it by a stochastic block model, and then look at the symmetries of the stochastic block model instead of the symmetries of the graph. And now you have many more symmetries. At least you have all of the permutations within each class. Also, you have the permutation that somehow keep the stochastic block model invariant. Okay, so now you have many more symmetries, and you're able to reduce the number of trainable parameters, and you overfit less, and you get very nice results. Okay. Okay, so in summary, and I continue to work on applications of this theory. So probably in the next couple of months, I'm going to publish more practical applications of the regularity lemma and using graph theory for graph neural networks. Okay, so in summary, we saw here that even though deterministic large graph signals may look complicated, they're actually regular and behave as if they were sampled from stochastic block models. We developed the graph-on-signal cut metric that has this interpretation that two graph-on signals are close to each other if they look like they were sampled from the same stochastic block model. This shows us that the space of, so under this metric, the space of graph signals is dense in a compact space. And on the other hand, message passing networks are Lipschitz continuous. And these two properties together allow us to prove universal approximation theorems and generalization theorems, sampling. Yeah. So if you're interested in this line of work, you can take a look at my papers. Okay, thank you.
Yeah, thanks, Ron. Any questions? So if you can put it in the chat, or you can unmute yourself. I see there's already one question in the chat on the message passing. So are you considering one hop, or is it multi hops? And could you extend it to multi hops if it's just one hop?
Well, I don't augment the graph in any way. For me, the graph is the computational graph.
No, but I mean I think in the neural network, right? In the message passing neural network. So you do one. It's basically you look just at your one hop neighbors, right?
In each layer, but then you have many layers, right?
Yeah, right.
The receptive field increases as more layers you have. If you have L layers, then you look at the L-hop neighborhood.
But I think there's also work that uses graph-on filters, right, in every layer, which would consider already multi-hops in one layer, right? So could you? I think the group of Alejandro Ribeiro at Penn.
So I suppose if you want to analyze such a method, you would need to. So such a method, you can think about it as augmenting the graph or changing the graph from the given graph to some computational graph, and then you need to see what is the corresponding graph on. For example, if you take the adjacency matrix and compose it on itself, then you need to do the same thing for the graph on. Suppose you get the same properties because the whole analysis doesn't depend on any properties of the graphon, right? So the graphon can be anything. It doesn't need to be continuous, doesn't need to be nothing. It's just a measurable function. So the analysis is not sensitive for a specific choice of a graphon. It works for any graphon. So whatever you want to do, right? You can use whatever graphon uses. So a graphon that has bigger neighborhoods, in a sense, you can also use such a graphon.
Related to this measure that you have on the slide now, isn't in the second term, isn't the supremum just always obtained when U is the full set? I mean, in the second.
No, because the absolute value is outside.
But the f is always positive, right? Or no, no.
It can be negative.
Yeah, right.
So even if it's positive, you subtract the
right.
positive things, right?
Yeah, right.
But you can get actually what you do. So U is going to be the support of the positive part or the negative part of
Right.
the difference.
Yeah,
And this is why it is equivalent to L1.
Right.
Okay.
Hi, Gert, can I ask a
Yes.
question, please?
That's fine.
So, thank you, Ron. I follow your work. I think it's so. I have a question regarding the sampling that you mentioned. You mentioned this bound square root 1/k, and it was kind of one slide. Could you comment a little bit more on when you talk about sampling?
This one?
Exactly, this slide. Yeah.
Mhm.
What are you like? What type of sampling do you consider?
Yeah.
This distance, what you do? You look at the induced graphon, and then you. I mean, could you elaborate a little bit on?
Okay. So what you do is first of all, the theorem is for graphons, but graphs are just a special case. In the situation of graphs, what you do is you uniformly sample the nodes with repetition and consider the subgraph. That's how you sample it. And in the graphon language, this is uniformly sampling points in the interval 0 to 1 and considering the sampled graph. And this is equivalent because in the case of a graph, you induce it to a piecewise constant graphon, and sampling points uniformly on the interval is exactly the same as sampling the nodes with repetitions.
So you sample the graphon. You don't sample the graph.
You sample the graph. You can sample, the theorem is for graphons, but a graph is a special case. So I can give you a graph of 10,000 nodes. Okay, you choose uniformly from 10,000 a node, let's say 100 times, and then you get a subgraph with 100. So you don't need to think about graphons, right? You can directly work with graphs.
Okay.
Because it's a special case of graphons. Okay.
Thank you.
Any other questions?
Well, maybe I have one. So, I'm interested in. So, first of all, thanks for the very nice talk. So, very interesting results. So, so in one of the slides, when you talk about the actually approximating the graph by the SVM, so you actually like have a bound on the number k, right? So, can you elaborate a bit more about that upper bounds on k? Yeah, maybe. Yeah.
Okay.
Yeah, so like what are the insights for this for the number intervals there?
Okay,
Right.
why is it 2 to something over epsilon squared? So the insight, the way it is proven is that first of all, you allow, so here all of the communities are non-intersecting in the partition. But in the proof, you start with communities that can intersect each other.
Okay.
Then you have something like 1 over epsilon squared communities or 2 over epsilon squared. The problem is that there is no, if they intersect each other, there is no way to sort the nodes into intervals because the intersection pattern is complicated. So then you look at all the intersections of all of the different sets, and you have 2 to the power of communities intersections.
Okay.
This is why you have 2 to the power here.
I see.
Once you have 2 to the power, everything is now disjoint, and once it is disjoint, you can just sort it on the line in intervals.
I see. Thank you.
Any other questions? I don't see any new in the chat, so if not, then I think we can wrap up here. So thanks a lot, Ron, for the nice presentation.
Thank you.
Interesting results. So then for the attendees, so we will see you next month in April with a new webinar. So thanks a lot for attending and see you then.